In this example, we're told we have a can of compressed R134A refrigerant. It's used as a gas duster. These gas dusters are sometimes called compressed air. They have cans that look like this. Even though it's called compressed air, it's really never compressed air. It's always some compressed other gas, like R134A. That's a pretty common one as a refrigerant. Early versions of this used to compress more flammable gases, like a butane, for example, or propane. But those, of course, were flammable, and so they tended to get away from that, went to other non-flammable gases. But R134A is a pretty common one. Anyway, it's used as a gas duster here, and it's discharged while in an upright orientation. And we're asked to estimate the initial rate. Let's go ahead and highlight the initial rate at which the specific internal energy changes within the can, and given the following conditions. And by the way, the conditions here, like the can volume, the mass of the refrigerant inside the can, the external temperature, pressure, etc., these are all typical numbers for a can that looks something like this. Okay, so these are all sort of real numbers. So when I look at this, I see that I'm trying to find the initial rate at which the specific internal energy changes. So that makes me think that we'll need to use the first law. So let's write out the first law. It's the time rate of change of total energy within the control volume is equal to the rate at which heat is going into the control volume minus the rate at which work is being done by the control volume plus the rate at which total enthalpy goes into the control volume minus the rate at which total enthalpy is leaving the control volume. Okay, and one thing to recognize is that this is an unsteady problem, right? So we're starting with a certain amount of mass inside this can, has a certain amount of internal energy within the can. And then as you open the, press the nozzle here and stuff comes out, so it'll come out of the nozzle there, then the mass inside here and the internal energy will change. So they'll be changing with time. And in fact, that's what we're trying to find is what's that initial rate at which the specific internal energy changes. So it's a transient problem. Okay, so now that we have the first law, we need to apply it to some control volume. The one that makes sense is one that surrounds the can. And we'll go ahead and start expanding our various terms in the first law. So first, let's start with the time rate of change of total energy within the control volume. That'll be the time rate of change of internal energy plus kinetic energy plus potential energy, all within the control volume. And the kinetic energy in here is not going to change with time because it has no macroscopic movement. It's, the can's discharging. It's not flying around. We're holding it in place. So that's going to be 0. And the potential energy in here will be basically 0. It may change a little bit because as you discharge mass, it's possible, and we'll see this later, but it's possible that this is not a uniform gas. In fact, often, well, most of the time when these cans are filled, there's some vapor at the top and liquid at the bottom. And so as you discharge it, that interface between liquid and vapor may change height, and that would change the center of gravity, which would change the potential energy a little bit, but it's such a small value that it's very reasonable to set that equal to 0. Okay? So then what we're left with is the time rate of change of the internal energy within the control volume. We're asked to find the time rate of change of specific internal energy, so let's expand that out into the mass times the specific internal energy within the control volume. And since the mass is changing with time and the specific internal energy is changing with time, I'm going to carry that time derivative through to both. So it'll look like this when I expand that derivative. Okay, so I have to include both since both the mass and the specific internal energy are changing with time. Okay, so that's this very first term. The heat transfer term, I'm going to set equal to 0. I'm going to put it about equal to 0. I'm assuming negligible heat transfer. That's an engineering assumption. Certainly there will be some heat transfer across this boundary, but I'm assuming that it's very small. So that's an engineering assumption that I think is reasonable, so I'm going to set that equal to 0. Work done by the control volume, well, that's at 0 because there's no other work crossing this dashed line other than the flow work coming out of the nozzle. So it's a rigid can, so there's no PDV work at these boundaries. There's no electrical work. There's no rotating shaft, nothing like that. So that term is 0. As far as the total enthalpy coming in, I'll just write it like that. That's going to be 0 because there are no inlets into this can. It's just an outlet. And for the outlet, I'm going to there's just one outlet, so I'm just going to call it m dot out. It'll be multiplied by the specific enthalpy out, so it's just this term. By the way, the HT is known as the total enthalpy, total specific enthalpy. It's just this collection of terms here. If you didn't know that already, it's just a shortcut way of writing all these terms. So the total enthalpy coming out, the rate at which total enthalpy is coming out, is going to be the mass flow rate out. That's just right here, m dot out. And it's the specific enthalpy of what's coming out plus the kinetic energy of what's coming out. That's the specific kinetic energy. I'm going to keep that term in there because I'm told what the speed of the discharging jet is. It's 11 meters per second, which isn't a small value. This quantity may be small compared to that, but let's just keep it in there since we know the velocity. It doesn't hurt to keep it. It may not be large in the end, but we know the value of it, so let's just keep it in there. But I will eliminate the potential energy term at the outlet because so I'm basically going to neglect that term because we're dealing with the can elevation is not very tall. You know, going from the center of, I mentioned before about the center of mass being about here within the can, you know, the height from there to the outlet is very, very small. And as you'll see later, that this is typically vapor that's going to be coming out here. So the density of it's quite small. The elevation is quite small. So the potential energy is really negligible. So we can reasonably drop that out of the equation. Okay, so now we can substitute back into the first law and simplify it. So let's do that. We have on the left-hand side the terms involving the mass within the control volume and the specific internal energy. By the way, it's this term that I'm trying to solve for. On the right-hand side, we just have the specific, we have the total enthalpy term coming out. I should put an out there. All right, so this is what we have now from the first law. Now, when I look at that, there's some mass terms that I'm going to have to deal with. First of all, there's the mass in the control volume. We know that. That was actually given. Initially, the mass in there is 284 grams. So that one's known. This one we're going to have to, that's what we're solving for. The specific internal energy within the control volume, at least remember I'm doing this initially, that I should be able to figure out because I know the properties initially. I know the initial can temperature and the initial pressure in there. So I should be able to figure that one out. The mass flow rate term, or I'm sorry, the time rate of change of mass within the control volume and the mass flow rate out, those I think will come from conservation of mass. So let me write out conservation of mass right here for that same control volume. Okay, so here, again, there is no inlet into that can, so that's 0. And the only outlet is just that one that we're calling m dot out. So the time rate of change of mass within the control volume is equal to minus m dot out. So I can take that and plug that in right there. Okay, so let me do that, and then let me rearrange the equation. So I'm going to do that all in one shot. So we're going to have m dot out. Oh, and by the way, I just realized I forgot a negative sign. There's a negative sign right here, and that negative sign should go right there. Okay, so I apologize for dropping that, but just make a note of it. Okay, so we have m dot out. This will be UCV minus H out minus 1/2 V squared out all divided by the mass in the control volume. Let me just look at that for a moment to make sure I've got all the signs correct. Yeah, I think everything's okay there. And so this is what I'm solving for, and specifically I'm trying to do this all, at the initially. So I'll put a subscript I there just to mean the initial case. So again, I know the mass in the control volume initially. That was the 284 grams. I know the velocity out initially. That's the 11 meters per second. Okay, so I'm getting some quantities so far. Let me focus on the specific internal energy in the control volume initially. So that's going to come from the property tables for R134A. So let me take a look at so I'm told initially the pressure within the control volume initially is 5.7171 bar absolute, and I know the initial temperature within the control volume was 20 degrees C. So I can use the property tables for R134A to get the other properties. Okay, and if you look that up, I'm not going to show it here, but if you look at the tables for those conditions, what you'll find is that the R134A is in a saturated liquid vapor mixture phase. Okay, so it's so saturated liquid vapor mixture phase, so we're going to have to try to calculate what the quality is for that case. Okay, so to find the quality, I can actually use the specific volume to find that. So remember that the volume of the control volume is given. That's the 295 milliliters. Let me mark that down, 295 milliliters. So since I have the mass and the volume, I can find the specific volume within the control volume initially. So that'll just be the volume divided by the initial mass. And when I do that, I'll get, let's see, what does that number come out to be? So when I do that calculation, it comes out to be 1.04 times 10 to the minus 3 cubic meters per kilogram. So what I can do is, since I know I'm in a saturated liquid vapor mixture phase, and that's the actual specific volume inside the control volume, I can then solve for what the quality is inside the control volume initially. So that looks like the following. Let me write it out, and then we'll discuss it. There. So I know so this is how I would find the quality initially within the control volume. It's the specific volume in the control volume, it's this term right here, minus the saturated liquid specific volume initially, and then in the denominator here, this one is the saturated vapor specific volume initially. So I can look those up again from this saturated liquid vapor mixture table for R134A. So let me just note those over here. So these come from the saturated liquid vapor mixture tables. So let's see. This one for the liquid is 0.000811610 cubic meters per kilogram. For the vapor, it's 0.03597 cubic meters per kilogram. Again, so these from the saturated liquid vapor mixture table at 20 degrees C. Okay, and I'll put the 5.7171 bar here as well. Okay, so now we can take these quantities, put them in here. Hopefully you know how to do this, right? This is stuff that you've done before. But you'll find that the quality initially comes out to be 6.33 times 10 to the minus 3. So the quality is very small, actually. It's can is filled mostly with liquid, but there is some vapor. And in fact, if I just kind of sketch out what the can looks like, here's the can with the nozzle. Here's where it's coming out. What it would mean is that we have a lot of liquid in here. So this would be a liquid phase, and this would be a vapor phase up here. Right? The vapor would be less dense, so it would sit on top. So that's important to know, actually, because when you discharge right up here, it's going to be discharging vapor rather than liquid. In fact, they tell you when you operate these cans, they tell you on the can to keep it upright when you pull the trigger on it so that you're discharging vapor. If you turn it upside down, then you'll be discharging liquid. And what ends up happening then is when you discharge the liquid, as soon as it comes out of that nozzle, so what I'm talking about is this. If you have liquid and the vapor there, but the nozzle's down here, when that liquid leaves the nozzle, it will rapidly flash into vapor as it comes out of here, and that'll drop the temperature to a very low temperature, and then it ends up, you can damage your electronic components because the temperature gets really, really low. And you could also hurt yourself. You could give yourself frostbite because the temperature is so low. So they tell you don't do this. Instead, keep it upright so that you're discharging the vapor. Okay, so getting back to trying to find the various terms in this equation, we were trying to get the specific internal energy within the control volume. Now that we have the quality, we can do that. So the specific internal energy in the control volume initially is going to be 1 minus the quality in there initially times the saturated liquid specific internal energy plus the quality times the saturated vapor specific internal energy. So again, these will come from the tables here. We can look these up. So when I look them up, let's see, this one was 78.857, and this would be kilojoules per kilogram. The exact values that you look up here for the specific internal energy, those will depend on the type of table that you use. So you might see little different, numbers that might be a little different from what I'm using, depending on the table that you use. But the difference should be the same. Like if I took the difference between these two numbers, it should be the same regardless of what table you use. Okay, so anyway, if we do this, then we can calculate the initial specific internal energy within the control volume, and that comes out to be 79.88 kilojoules per kilogram. All right, so we're making good progress. So now we've found the mass within the control volume. We know the mass flow rate out. We haven't calculated that one yet. We're going to have to find that in just a moment. But we do have this one. As far as finding the specific enthalpy coming out, well, when we refer to this picture, you'll see that that specific enthalpy coming out should actually be the specific enthalpy of the saturated vapor. So we can look that up in the table. It's the specific enthalpy of the saturated vapor at that temperature and pressure. And let's see, when I look that one up, what did I get? That'll be 261.60 kilojoules per kilogram. Again, it depends on what table you use. So that's, I'll just make a note here, H out is the specific enthalpy of the saturated vapor initially, which is the 261.60 kilojoules per kilogram that we find in the table. All right, so now I have everything in parentheses here. I have the denominator. Let's go ahead and talk about the m dot out value, right? That's this mass flow rate out right there. So the mass flow rate out we can find as the volumetric flow rate coming out, which would be the velocity out times the area out divided by the specific volume out initially, right? So that's how we would find the mass flow rate coming out initially. And the velocity out, we know, that's given right up here. It's the 11 meters per second. The area out we're given. So let me just make a note. This is 11 meters per second. This is the 1 square millimeter that we're given back here in the problem statement. Okay. And then the specific volume of the R134A when it's coming out, remember that'll be the specific volume of the vapor. So this will be equal to the specific volume of the vapor, saturated vapor initially, which we know that's this quantity right up here. Right, so remember, it's just saturated vapor coming out. So when we solve for the mass flow rate out initially, that'll come out to be, let's see, 3.0558 times 10 to the minus 4 kilograms per second. So now we finally have everything we need to calculate what the time rate of change of the specific internal energy inside the control volume is with respect to time. So when we do all those calculations, we'll get this to be minus 8.72 times 10 to the minus 2 kilojoules per kilogram. And that whole thing is divided by time, seconds. So this is just like kilojoules per kilogram second. So that's what we were looking for. So you can see that the internal energy within the can is decreasing, right? It's getting smaller, which you can imagine that would also mean that the temperature is dropping inside that can as well. And that's something that you just know. You just know from experience, if you've ever, pressed on the lever of this can and you kind of just discharge it all at once, you'll feel that the temperature in the can actually gets colder as a function of time. And even though we didn't specifically look at how the temperature changes, we can, it's pretty reasonable to assume that, if the internal energy is decreasing with time, the temperature would be decreasing with time too. To actually do the calculation for how the temperature is changing with time, it turns out to be a more complicated analysis, one that we're not going to go through here, but it is possible to see how the temperature varies with time. It's just more complicated than what we can do here. Okay, well, hopefully you're able to follow all the parts in this. This was actually a more complicated example. It's a transient problem involving the first law. And we kind of simplified things down. We made use of conservation of mass along the way. And we had to find properties. That was kind of a more challenging part of the problem. And one key part of the problem is recognizing that it's in a saturated liquid vapor mixture phase, but what's happening is the vapor's on top and the liquid's at the bottom. So when you discharge the can, it's discharging just the vapor. So that's a key part of this problem. And then one other thing we had to do here was calculate a mass flow rate. So, okay, hopefully you understood everything going on here. If you did, you're doing pretty well. So we'll end it there.